Good day everyone. Today, we're going to continue our discussion about vector spaces. Vector spaces. We are going to define vector space and recognize some important vector spaces. Show that a given set is not a vector space. What is a vector space? Let V be a set of which two vector operations, vector addition, and a scalar multiplications are defined. If the listed axioms are satisfied for every u, v, and w in V, and every scalar or a real number c and d, then V is a vector space. For addition, 1. If u and v are vectors in the vector space V, then u plus v must be in V. So this is the closure under addition properties. Let u plus v is equal to v plus u. So if u and v commute, so u plus v is equal to v plus u. So that's commutative property. U plus v plus w is equal to the quantity of u plus v plus w. So that's associative property. V has a zero vector 0 such that for every u in V, u plus 0 is equal to u. So that's the additive identity. For every u in V, there is a vector V denoted by negative u such that u plus negative u is equal to 0. And negative u is the additive inverse. For scalar multiplication, if you're going to multiply the vector u by a constant, the product c times u is in V. So this is our closure property under scalar multiplication. C times the quantity u plus v is equal to cu plus cv, distributive property. C plus d times u is equal to cu plus du, again another distributive property. C times the quantity du is equal to cd times u, so that's associative property. And the scalar identity 1 times u is equal to u. So if all of these 10 properties are satisfied, then we say that the vector operation of scalar multiplication and vector addition forms space. Now, let us have this example. Show that the set of all 2 by 3 matrices with the operations of matrix addition and scalar multiplication is a vector space. If A and B are 2 by 3 matrices and C is a scalar, then A plus B and CA are also 2 by 3 matrices. So if we have A, B, C, D, E, F, we add this into another matrix A prime, B prime, C prime, D prime, E prime, F prime. So the result is still a 2 by 3 matrix. So A plus A prime, B plus B prime, C plus C prime, D plus D prime, E plus E prime, and F plus F prime. So if we're going to apply addition, vector addition, the result is still a 2 by 3 matrix. While if we're going to multiply it by a constant k, like in the case of A, B, C, D, E, F, so the closure property of multiplication, Ka, Kb, Kc, Kd, Ke, and Kf is satisfied. So the set is therefore closed under matrix addition and scalar multiplication. Moreover, the other 8 vector the other 8 vector space axioms follow directly. So the set is a vector space. Vectors in the space have the form vector A equal to A11, A12, A13, A21, A22, and A23, where A sub ij is a real number. Now let us consider a continuous function. Let the continuous function c, which is defined over the set of real numbers from negative infinity to positive infinity, be the set of all real valued continuous functions defined on an entire real line. This set contains or consists of all polynomial functions and all other continuous functions on the entire real line. For example, we have f of x is sine x. So this would be your f of x. And then your g of x is an exponential function. Are members of this set because f of x and e raised to x are both continuous functions. So addition is defined by f plus g of x. Thus, f of x plus g of x is also defined, as shown in the right. Scalar multiplication is defined by c times f of x or c times f of x. And that shows that the continuous function from negative infinity to positive infinity is a vector space. So as you can see here, there is a multiplication or there is addition. So therefore, it is a vector space. So to verify that the set C from negative infinity to positive infinity is closed under addition and scalar multiplication, let us use the results from calculus. The sum of two continuous functions is continuous, and the product of a scalar and a continuous function is continuous. To verify that the set C from negative infinity to positive infinity has an additive identity. So additive identity, so that's the inverse of the function. So if you're going to add it to the negative of that number, the result would be 0. So consider the function f sub o that has the value of 0 for all x, that is f sub 0 of x is equal to 0, so where x is any real number. This function is continuous on the entire real line. So that is basically the line y is equal to 0. So that's the horizontal line. And it is part of the continuous function. Moreover, if f is any other function that is continuous on the entire real line, thus f plus f sub 0 of x is equal to f of x plus f sub 0 of x, where f of x plus 0 is equal to f of x. So if we're going to add this 0 vector or 0 function to another function, then the result is still the original function. This shows that f sub 0 is the additive identity in the continuous function from negative infinity to positive infinity. The verification of the other vector space axiom is left for you to finish. Now, to summarize all the vector spaces, we can have the vector space, the real number R, which is the set of all real numbers, R squared, which is the set of all ordered pairs. So that would be the set of the set of all vector pairs xy. Ordered triple x, y, z. We can have ordered n tuples, which is composed of n elements. And then the continuous function c of negative infinity to positive infinity. We can have a bounded continuous function c from a to b. So it is only defined or it is only continuous from a to b. We can have the set of polynomial. So p is a set of polynomial. So we can have that p to be equal to a plus bx plus cx squared plus dx cubed, and so on. P sub n is of order n. So that would be a plus bx plus cx squared plus, let's have it as f x raised to n. And then we have the order m by n matrix. So this is any rectangular matrix. And then we have the square matrix, an n by n square matrix. All of these are vector spaces, provided that we're going to use the conventional vector addition and scalar multiplication. Let us consider the theorem 4.4, which is about properties of scalar multiplication. Let V be any element of the vector space V, and let C be any scalar. Then the properties below are true. 0 times the vector, or 0 times any vector, is a 0 vector. And a constant multiplied to the 0 vector is a 0 vector. So since this 2 is equal to a 0 vector, if you are going to have a product which is a 0 vector, it means that either C would now be equal to 0, or the vector V is equal to the 0 vector. If we will be multiplying -1 to the vector, we're going to have the identity element of the vector. Now let's consider the set that is not a vector space. Let us consider the set of all second-degree polynomials. The set of all second-degree polynomials is not a vector space because it is not closed under addition. So just to simplify that, let's have f sub 2 of x to be equal to x squared. And let's have g sub 2 of x is equal to negative x squared. If we're going to add f sub 2 and g sub 2, the answer would be x squared plus negative x squared, which is 0. And 0 is not an element of p sub 2. So since 0 is not an element of p sub 2, then we say that it is not a second-degree polynomial. So therefore, there's no closure under second-degree polynomials.